Are we ready to move on?
Start over.
Okay. Pipe network analysis. And there are a lot of practical applications here, whether you're of course the classic one is analyzing municipal water distribution system. You're building a residential neighborhood and you're extending the pipe system, and you need to know how that impacts pressures throughout the system. I want a certain pressure at my house, and if the system expansions decrease that below what it ought to be, I'm concerned, and so you want to maintain your pressures throughout your municipality and flow rates, and so the municipal water distribution system is a good example, but maybe a sprinkler system for a golf course, a sprinkler system for fire protection in buildings. There's all kinds of water distribution systems that involved a large number of pipes. And we're interested in knowing what the pressures and flow rates are throughout the system for given demands and supplies of water. And the basic concepts for any system are cited here. And when we're dealing with pipe network analysis, if you look at any junction where two or more pipes come together, the discharge coming in minus the discharge going out is the external flows. That's just the continuity, conservation of mass. Inflows have to equal outflows at any junction. And then if you look at the loops, for any closed loop, the head losses and the head gains have to sum to zero. And so the sum of the head losses have to sum to the sum of any the heads added by the pumps. If there are no pumps, the head losses have to sum to zero. And this example gives us a system we can work with, and so this system has only 6 pipes in it, so you use your imagination and assume there's 500 pipes in the network, and the basic concepts are just as valid for 500 pipes as for 6 pipes. But the problem...
Before you get into that, on these problems now, will there be a standard factor for minor losses, or do you just assume away minor losses when you get to this level now?
As far as the way you would actually handle it, it can be done different ways. A very typical way would be to come up with an equivalent length of pipe, and we were talking about equivalent pipes a few minutes ago, and you can just add an equivalent length of pipe for minor losses. That's not unusual, but the system allows for including minor losses as well.
Okay.
Let's see. We're determining the discharge in each pipe and the hydraulic grade at each junction. And the hydraulic grade at junction D is given as 400 feet, and the external demands are shown. And we're using a Darcy-Weibach friction factor of 0.023 for all the pipes. And all the pipe characteristics are provided in the table. So what the table basically does, it takes the length of the pipe, the diameter of the pipe, and plugs into the expression from the Darcy-Weibach equation to get a K. So we're going to express each pipe as a K. And if we had valve fittings, say valves or other fittings in the pipe, we could put the K for the minor losses right in with that K. And so that K could express valves and bends and contractions and so forth as well. In the example, I just use the straight section of the pipe. But from now on, the K is our expression for the loss characteristics of that section of pipe and anything that's in it. And what we'll actually do, there's 2 parts of the analysis. One is to compute the flow rates in each of the pipes. And we'll do that first. And you've got to know the flow rates to be able to compute head losses. And then after we know all the flow rates, we'll come back through, and given the hydraulic grade at one location And then knowing the flow rates to compute the head losses, then we can track back through the system and compute the hydraulic grade at every location in the system. So first we'll compute head losses, first we'll compute discharges, and then come back through to compute the hydraulic grade. And so there's a lot of different ways of doing this. The basic concepts are very simple. The concepts, and let me repeat the basic concepts. At each node, at node A, the inflows equal the outflows. At node B, the inflows equal the outflows. At any node, continuity is maintained. The inflows equal the outflows. The second concept around any loop, and we're looking at 3 loops here. We could call this a loop, we could call this a loop, we could call the big one a loop. But for any closed loop, the sum of the head losses have to sum to 0. If you have pumps, then it's the sum of the head losses and the head gains, keeping track of signs, have to sum to 0. That's all there is as far as basic concepts. What makes this complicated is we get lost in the computations. We got to do some number crunching. And so the concepts are the same, and the different ways that people have gone about solving pipe network analysis problems, the differences relate to computational details. And of course, computational details are quite significant part of the problem. But here's the system, and you'll notice on the previous diagram I expressed the external demands in gallons per minute, because the 500 gallons per minute, 300 gallons per minute, and so forth, that's typical units, but to be able to plug into our equations, we need consistent units, so we've converted everything to cubic feet per second. And so we've got the given demands in cubic feet per second, and we've got the pipe characteristics expressed by the Ks, and I've got to make an assumption to be able to lay out the equations and so forth, and that's the direction of flow. And so you'll notice the arrows, that's a direction of flow, and those may be incorrect. And if they're incorrect, when we get the final answer, the Q will be negative. And so the basic approach is to get started by assuming a direction of flow in each pipe, and then when the computations are all done, if you get a negative flow just means that your initially assumed flow direction is opposite to what it should have been. And so we've got our Ks, we've got our external demands on the system, and of course we've got to have some supply. So we've got some tank here, and by the way, the water surface elevation in that tank is going to be 400 feet when we do the hydraulic grade computations. But here are all the demands. People are taking water out of the system. Maybe this is a water main, and these are just sub-portions of the system that's taking water from the main. And so when you add up all of the external flows, they've got to add up to the flow coming in. You got to maintain continuity for the entire system as well as each junction in the system. And we're going to need some sign conventions, and doesn't matter which way we do it, but when we're maintaining continuity at a junction, let's just say that flows coming in are plus, the flows going out are negative. And when we're summing head losses around a loop, let's just say clockwise is positive and counterclockwise is negative, just to have a consistent convention. And now you can write equations, and so just set the diagram aside and refer back to it, and these are the equations, and the unknowns are the flow rates. We got 6 pipes, so we're trying to compute the discharge in each of 6 pipes. So Q1, Q2, etc. are the unknowns. And so there's 6 pipes, so we need 6 equations. And so we can maintain continuity at the nodes. And so at junction A, we've got the flow, at least the way I've assumed the flow is indicated by the arrows. The flow in pipe 1 goes into junction A, and my sign convention is call it positive. The flow in pipe 5 leaves junction A. My sign convention says call it negative, and then the external flow is 1.12 cubic feet per second. My sign convention calls it negative since it's leaving junction A, but by the time I put it on the right side of the equal sign, it's a positive number. So that's the mass balance, the continuity equation for junction A. And then you can go junction by junction. And junction B, the flow in pipe 1 leaves junction B, I'll call it negative. The flow in pipe 2 enters junction B, I'll call it positive. The flow in pipe 6 enters junction B, I'll call it positive. The external flow of 0.67 cubic feet per second, the demand that's coming out of that is leaving it, and I'll call it negative, and then flip it over to the other side of the equal sign. So of each junction, you maintain continuity, and you can write an equation at each junction. Now for each loop, and there's 3 loops, and I just chose to use 2 of the loops, and I guess the rule is you got to choose loops so that every pipe is in at least 1 loop. And so loop 1, we write head losses. Head loss is KQ squared. And so loop 1 involves pipe 1. The flow is counterclockwise. My sign convention is to let clockwise be positive, so I'm going to call it negative. And then pipe 6 is in that loop. Well, let's see, I did pipe 4 next. Pipe 4 is in the loop, and it has a K of 30.77 times discharge in pipe 4 squared, and that's going in a clockwise direction, so I'm going to call it positive. Pipe 5 is in the loop. The flow direction is counterclockwise, I'll call it negative. The K is 5.763, and so the head loss in pipe 5 is 5.763 Q5 squared, and then pipe 6 is, in this particular loop, it's counterclockwise, and so I'll call it negative. The K is 4.053 Q6 squared, gives me the head loss. And so that's summing the head losses in that loop, and then I sum the head losses in the other loop, and that gives me 6 equations with 6 unknowns. I could write more equations, but they would be redundant. And so all I've got to do is solve those 6 equations for those 6 unknowns. If I had 500 pipes, I would have 500 equations and 500 unknowns. And the thing that complicates this just a bit are those little superscripts, because there are linear. If you've got a system of linear equations, there's straightforward algorithms and computer software to solve systems of linear equations. But we've got, some of our equations are nonlinear. And anytime you have nonlinear equations, you've got to solve them iteratively. And so when you've got a system of equations, some of which are linear and some of which are nonlinear, there's no direct solution other than a number of different algorithms, all of which involve iterative type computations. Now the reason that there are different computer codes and different approaches for solving pipe network analysis problems is that they solve the system of equations differently. And we're going to use the old classic equation, and it's called the Hardy-Cross method. And well, before we go into the Hardy-Cross method, we'll be leaving these equations, and but the point here is, once you've got the equations, any system for solving a set of nonlinear equations would solve the problem. Now the Hardy-Cross method, what it does, it solves one of the loop equations at a time. And so however you go about it, it's going to be iterative, but it does this loop equation, then solves this loop equation, and it does it in such a way where it's maintaining continuity at the nodes. And so we take a look at the Hardy-Cross method, and what the Hardy-Cross method does, it's an old method, it's still widely used, but it's the one method that you can do with a calculator, where you can do a loop at a time. And it's presented in the engineering reference manual in the fluid mechanics chapter, and the basic equations given here. And so what we're going to do is well, by definition, we don't know what Q, we're trying to solve for the discharge, we don't know what it is. And so what we're going to do is assume a discharge to get started, And then as we iteratively go through the process, we're going to keep updating that discharge. And so QA is an assumed flow. It's our best estimate so far in the iterative computations. Now the true flow, which we don't know, we're trying to solve for that, is Q. And so at any point in the iterative computations, we're off by Q minus QA. And so delta is going to be an estimate of the correction factor. And so the true flow is our assumed flow plus the correction factor. And we know around any loop the sum of the head losses sum to 0. And so the head loss is K times Q to the N. And the Q, the actual true Q, is an assumed Q plus the correction factor, how much we're off. And so that equation is the basic concept of maintaining conservation of energy in each of the loops. Now you can go through some algebraic manipulation, which takes some time in some algebra, some significant mathematical manipulation, in which you solve for delta. And when you solve for delta, you get this expression, and that's the Hardy-Cross equation. And so what you're doing with the Hardy-Cross equation is that for your best guess for the Q's in each pipe, you plug in, compute a delta, use that delta to update the Q's, and keep doing it over and over until the deltas go to 0. And once the deltas go to 0, there is no error, and you can stop. So we've reproduced the Hardy-Cross basic equations on this sheet along with our the network in which we're solving for. And so to get started, for example, in the KY pipe program that so many people use, the program automatically assumes 1 cubic feet per second in every pipe and starts from there. In many computer software packages, the user has to enter the initial guess. We're doing things manually using a calculator, and about the only way to do it using a calculator is set it up so that you, the user, is making an initial guess. And so these are my initial guesses. They're arbitrary, but they're not totally arbitrary. We've got to maintain continuity at each node. And so I've written on each pipe an initial guess of what I think the flow in that pipe might be, the 2.43 CFS. Now, that was arbitrary except for this. I've got to maintain continuity. And so you can start any place in the system you like. And, well, let's start here at node D. Now, at node D, we've got pipes 6, 3, and 4. And so coming in from the storage tank or the water main or whatever the source of supply is, we've got 8.96 cubic feet per second. So the flow in pipes 4, 6, and 3 have to add up to 8.96. So it's arbitrary what the numbers are as long as they add up to that amount. And so when you come to D, or node E, junction E, let's say, well, we got given 4.93 in external demand, that's leaving that junction. And if we got 2.43 cubic feet per second, which we arbitrarily assumed in pipe 4, well, we know that we've got to maintain continuity. And so if we've got 2.43 coming in and 4.93 coming out, this pipe has to provide the other 4.93 minus 2.43 is equal to 2.50 cubic feet coming into the junction. So if you're with me there, this is arbitrary. These are not the right answers. These are initial guesses, but the point I'm emphasizing is that they do have to maintain continuity at each and every node. Inflows have to equal outflows at each and every node. And if that's true at the very beginning, you'll maintain continuity just by the way the algorithm's set up as you go iterative throughout. So we've got the initial guesses of the flows. They're off by some amount, and the Hardy-Cross equation lets us estimate loop by loop. Now, as we estimate loop by loop, we're going to get the correction factor is not going to be quite right because you cannot ignore the other loop. But to make the computations trackable in the Hardy-Cross method, it's applying the equation to each loop independently of the other. And so, to get the correction factor for loop 1, the first loop, we got to sum up the head losses in that loop. And so we're summing up KQA. And so the pipes that are pertinent to loop 1 is pipe 1, pipe 6, pipe 4, pipe 5. The sign convention is clockwise is negative, clockwise I think we set up as positive, counterclockwise we set up as negative. As long as we're consistent on our sign convention, it could be either way. And so when we write this equation, what we're going to write is we're going to put the negative sign and then we're going to sum them up. So it's going to be K1, which is 2.895 times 3.62 squared, and that's counterclockwise, so it's going to have a negative sign in front of it. This is counterclockwise, so it's going to be negative K6 4.053 times 3.40 squared. That's clockwise, so it's going to be positive 30.777 times 2.43 squared. This is counterclockwise, so it's going to be negative 5.763 for K5 times 2.50 cubic feet per second squared. So those four terms are added together to get the top term of this expression. And, well, by the way, I've written the expression in its general term, realizing we're using Darcy-Weibach for head losses. I know the N is 2, so I've written it for N equal 2 here. We add up the four terms, and then we've got 2 times the sum of the absolute value, meaning the signs don't matter for the bottom part of the expression. So it's K times Q. It's 2.895 times 3.62 plus 4.053 times 3.4 plus 2.43 times 30.77 plus 2.5 times 5.763. That's going to give us a correction term for loop 1. And then we do the same thing for loop 2. Loop 2 has 3 pipes, so we're summing the head losses in 3 pipes, and then we've got the same expression for the 3 pipes here. And so having done that, and these tables set up the numbers, when we do it the first time using those initial guesses or initial estimates, I wrote the term guess one time in a paper, and the reviewer told me engineers don't guess, they estimate. So I should use the term estimate instead of guess, I guess. But using the initial estimates for the Q's, the correction factors came out to these 2 numbers. And then the way you correct, you just take the initial guess for the Q and add it to the correction factor. Now there's one pipe there. It's numbered pipe number 6. It's in loop 1 and loop 2. And so when you're doing the corrections, you correct that pipe twice. And you keep track of signs. And so in the first loop, the pipe 6 is counterclockwise, so the flow has the 3.40 cubic feet per second has a negative sign in front of it. But when you're in loop 2, that same pipe 6 is counterclockwise, so the 3.4 cubic feet per second initial guess has a plus sign in front of it. And so the correction factors came out negative, and so they're going to have a negative sign in front of them. And so you take the corrections, and when you correct the flows, you get another set of flows. And the way I've set up these tables is that we got a new set of flows, and then we take that new set of flows and we plug it into the Hardy-Cross method again, do the same computations over, and we'll get another set of correction factors. We plug into here, correct the flows, we'll get a new set of flows. And then as we go, finally the delta goes to 0, and as the deltas go to 0, the flows stay the same. And I get carried away with significant figures, and I probably carried this at least one significant figure too far, but I wanted to show that we can, with all four significant figures, get to the point where the delta goes to 0, and so it did. And so the final answer is that the Q in each pipe is given here. In the first pipe, it's 3.904, second pipe, and so forth. And that was awfully quick going through that. But what I've done is taken this last column of the flows and then transferred that back to the diagram, and so the diagram is showing the flows in each pipe. All the flows in the final computations are positive, and so that shows me that my initial assumed flow directions were correct. If I had a negative number in the answer, it just means to reverse the flow direction, and I'm okay. So now that I know the flows in each pipe, I'm interested in computing the hydraulic grade. And to be able to compute the hydraulic grade, you got to know the grade at one location. And in this problem at junction D, and the grade might be, you can visualize it as a water surface elevation in a storage tank. Or you could visualize it as the hydraulic grade in a larger water main, which is feeding this subset of the overall system. Either way, we've got the discharge and the hydraulic grade given at junction D. And so knowing the energy head at D, all I've got to do is compute the energy head in each of these pipes. Now the head at C will simply be the head at D minus the head loss in pipe DC. The head at B will be the head at C minus the head loss in pipe 2. Or saying that another way, the head at B will be the head at D minus the head loss in pipe 6. The head at E will be the head at D minus the head loss in pipe 4. The head at A will be the head at E. It's not going to be a head loss because head loss is in direction of flow, so it's going to be the head at E plus the gain in head, a negative head loss, in pipe 5. And so that's what we're doing in these computations. We're just starting at the known head of 400 feet at junction D and then running through the system. And so the junction C is connected with junction D by pipe 3. The flow direction is from D to C, and so the head at C is just the head at D minus the head loss in pipe 3. We compute the head loss in pipe 3 by saying KQ squared. We know the K for the pipe. We just finished computing the discharge rate. And by the way, that's another reason I carried it out to 4 significant figures so that I could get the head losses as precise as possible. And so that when I come down here and go through 2 different directions, I do get the same head at different points regardless of the route that I traced my head losses through the system. And then you just trace yourself through the system. The head at any location is the head at some adjoining location minus the head losses in the pipe connecting the 2. And you can trace yourself through, and the head losses are always K times Q squared. We always know the K. We just computed using the Hardy-Cross method the Q's, so we can plug in and we can get the heads throughout the system. And again, there's a bit of number crunching there, but make sure you understand that basic concept of what you're doing. Well, I can't draw the whole scheme of all the pipes, but I did draw a couple of the pipes so we can draw the hydraulic grade. And so the pipes I chose to draw was the pipe connecting D to E and the pipe connecting D to C. And I just plugged in the numbers we computed. And from D to C, we had a flow rate we computed using the Hardy-Cross method. It came out to 3.202 cubic feet per second. And then we computed the head loss by just taking that flow rate, squaring it, and multiplying it by K to get 1.5 feet of head loss from D to C. And so if we've got 400 feet of head here, and we subtract off the 1.5 feet of head loss, we get the head there of 398.5. And here in pipe, the flow from D to E in pipe 4, we computed using Hardy Cross the flow rate. Then we said the flow rate squared times the K gives us a head loss, very significant head loss of 141.7 feet, and then we subtracted that from 400 feet to get the total head there. Now, a couple things. One thing is that, and this is very common, this is what I've just presented is the conventional way of civil engineering of both textbooks and in process of doing computing hydraulic grades. But really, head loss is not a difference in hydraulic grade, but it's a difference in the total energy, which includes the velocity head. And we've sort of ignored the velocity head from that perspective, and that is a bit of a simplification. But what happens in most systems is the velocity head is relatively minor. And to illustrate that for this system, I went ahead and computed the velocity heads. And the velocity head in pipe 4 comes out to be 0.59 feet, which is relatively small compared to the total heads we're talking about. The velocity head in pipe 3 comes out to be 0.016 feet, which again is very small compared to the total heads. So what's missing here? What if you wanted to know the pressure head? If you're interested in the pressure head in the water main in front of your house, what additional information do you need to know? Let's say that your house happens to be sitting there at point C, and you're interested in maintaining pressure, because if you don't have enough pressure, it's hard to water your grass, and you don't get enough water coming out of the faucet when you take a shower. So what's missing that I need to know pressure head? Need to know the elevation. And so what I'm showing is just the hydraulic grade, and remember, by definition, the hydraulic grade is the elevation head plus the pressure head. And this is just total head above some datum, and so if you've got the elevation head above some datum, if you subtract the hydraulic grade from the elevation, let's say the datum is mean sea level. That's how maps are usually set up. It could be any other reference. And if your datum's mean sea level, and so the hydraulic grade is 398.5 feet above mean sea level, and then you know the elevation of the water main, if you want the pressure at the water main, or the elevation of the faucet head on your shower, if you don't want to know that point, you subtract the elevation from the hydraulic grade, and you get the pressure head. So pressure head is the elevation head plus the pressure head. Sorry, the hydraulic grade is the elevation head plus the pressure head. But we went through that pipe network analysis problem pretty fast there. Okay. Well, let's look at pumps. We've looked at different aspects of pumps, but let's continue here. And the basic concept here is that there's two relationships between discharge and head. And well, we've been talking about the discharge head relationship for a piping system, and we're going to continue to do that. We're going to call that a system head curve. But also for a pump, pumps are designed differently. Different pumps have different relationships, which we call a head capacity curve for the pump, and the manufacturer establishes that curve, and it's based on laboratory testing of the pump. And when you purchase the pump, the manufacturer has catalogs that provides head capacity curves for the pump. And so we're putting these relationships together, and a good way to do that is just in terms of an example problem. And so in this example problem, we've got these two reservoirs connected, and basically the reservoirs are just saying we've got two known heads, and we could express the head different ways, but an easy way to visualize it is we're pumping water from one reservoir to another. Now the water surface elevation difference is 100 feet between the two reservoirs, and we know the characteristics of the pipe. The pipe's 850 feet long, it's 6-inch diameter pipe. The friction factor is 0.02, so that characterizes the pipe. And we need the pipe characteristics to be able to express the head loss versus discharge relationship for that system, because what the pump's going to have to do is going to have to overcome this pumping lift of 100 feet plus the head losses in the pipe. And the head losses in the pipe are going to be a function of the flow rate in the pipe. And the flow rate in the pipe, what we're trying to solve for in this problem. And so we want to compute the discharge in this system, and what we're given is a pump characteristic curve. Now the pump characteristic curve, we've got a head capacity curve. And what it says is that at zero discharge, this pump can take care of a head of 160 feet. So if this 100 feet happened to be 160 feet, we'd have zero discharge. It would just hold that, but not pump. Now, if you have less head to overcome, if you ask the pump to overcome less head, it can pump at a larger flow rate. For example, it looks like at a head of 120 feet, it could pump 600 gallons per minute. At a head of only 60 feet, it could pump 1,000 gallons per minute. So there's a relationship between the head that has to be overcome by the pump and the flow rate through the pump. That's given to us by the manufacturer of the pump based upon laboratory testing of the pump itself. And he may hire an independent testing lab. And so when we're selecting a pump, we'll have to look at the head capacity curve for that pump and use that to see if it does what we want it to do as far as the pumping requirements of our system. Now, efficiency refers to the ratio of the electrical energy to the hydraulic energy provided by the pump. And you have to pay for electricity to run the electric motor that runs the pump, so you'd like to be as efficient as you can. And so the efficiency will vary with discharge. For different discharge rates, there'll be some point that's more efficient than other points for that particular pump. And so what we got plotted here again is we've got head versus capacity, a head capacity curve, and then we've got efficiency, which is that efficiency in the power equation we looked at some few minutes ago, versus discharge to get the efficiency curve. And the question in the problem is, for that particular pump, characterized by that particular head capacity curve, how much water is being pumped from the lower to the upper reservoir? Now, we can...
If you're doing this in reverse, and you're picking a pump to meet a given set of constraints, do you like to operate this for the efficiency and the head capacity cross there? Is that the overall system optimization? You know, often on these curves, you're looking for optimum points.
Yeah, it really isn't, though. The optimum point is right here. Right here, you've got an efficiency of 82%. That's the highest efficiency you can get with this pump.
Okay.
And so to get that 82%, what you've got to be pumping, and I'm reading the numbers off roughly, is something in about 600 and something gallons per minute. And if you're pumping 600 and something gallons per minute, you come up to that curve, and that's going to be at a head of 120 something feet. And we're going to continue with that basic thought as we go here. Okay, now this is the system itself. We're putting together two relationships. One is the pipe system, and then the other is the pump characteristic. And so in this system, and just any system in which you're pumping between two reservoirs or between 2 points of known head, you're overcoming some delta Z, some lift there, and then you're also overcoming the head losses through the system. And so to relate this back to the energy equation, we've done this in several contexts this evening, and doing it one more time, let's write the energy equation between point 1 and point 2. Those are points in the water surface elevations of the lower and the upper reservoir, the downstream and the upstream reservoirs. And so when we write the energy equation, and so at this point the elevation head's going to be some Z1, and we're using our traditional conventional gauge pressure, so atmospheric pressure is 0, pressure head is 0 at the water surface. The velocity head in the reservoir we're going to say is 0, very little movement in a large reservoir relative to this pipe anyway. And then the head provided by the pump is equal to the Z2 plus 0 pressure head plus 0 velocity head plus the head loss between points 1 and 2. And so the head provided by the pump is the delta Z, the Z2 minus Z1 plus the head loss in the system. So that tells us, using the energy equation, what we can pretty well visualize just intuitively, that the head provided by the pump has to overcome the lift, the delta Z, and it also has to overcome the head losses in the system. And that's going to always be the case in this example or other examples. Now what complicates it a bit is that the head loss is a function of the discharge. And also the head that the pump can overcome is a function of the discharge. And so we call this our system head curve. And so the system involves this delta Z, and it involves head losses in the pipe. And so in this problem I've ignored minor losses, but there'd be absolutely no problem in adding minor losses. We just express them as a K times the velocity head for the entrance and the exit if we wanted to, and any other minor losses that might be in the system. But in this example I'm just saying the head losses are the losses in the pipe, and so I'm relating the head losses to the flow rate using the Darcy-Weibach equation again. So I've written the Darcy-Weibach equation for the head losses, and then I've plugged in all the numbers into the Darcy-Weibach equation. And the only thing we don't know, everything's given except the flow rate. And so we've got the head to overcome by the pump is the lift of 100 feet plus, using Darcy-Weibach equation, a 13.694 times the flow rate in the pipe. And I'm using a graphical solution here. And so I want to plot up this head curve, so I just made up a table so I can plot it up. And so for different flow rates, I use Darcy-Weibach, and to have units consistent, I need the flow rates in cubic feet per second. Municipal city-type engineers often think in terms of gallons per minute, so our curves were expressed in gallons per minute, and so I use the conversion factors to convert gallons per minute to cubic feet per second. And then if you'll plug in these cubic feet per these flow rates, if you plug in 0.445 cubic feet per second in for Q, you'll get a head of 102.7. If you plug in 0 for Q, you'll get the pump head of 100 feet. And so for any Q, any of these Q's, we plug into the equation and get the pump head. And I did that so I can plot it up. Okay, and so here are the numbers we were just looking at from the table. There's 0 Q, the head's 100 feet. If there's the next number from the table, and here are the points we just computed. Those are computed points, and those characterize the piping system. The pipe's so long, it has so much diameter, the lift is so much. We call that the system head curve. And that is a good curve. That's a good number, and it's a good expression for head versus discharge for this system. Now the pump has a relationship between head and capacity. And we already talked about that, and here it is. That was established in a laboratory by the manufacturer in a hydraulics lab, and so that's a good relationship. These are both good relationships. And so they both have to hold simultaneously. And there's only one point on here where both relationships hold simultaneously, and that's right there, where the two intersect. And they intersect at a discharge rate, I think I read it off to be 630 gallons per minute. So we got a flow rate of 630 gallons per minute going through that piping system. If we want to know the head at that discharge rate, the head is, we can read across here, and it reads off to whatever it reads off to be here. Looks like about 120 feet. Now, we want to know the efficiency. Let's see, the flow is 630 something, and so we read up there, and as it turned out, it's pretty close to the best efficiency point. That's somewhat coincidental, of 83%. And so the answer is 630 gallons per minute is flowing through the system. And the head's going to be the 100 feet is just the delta Z, that's with no flow at all. And then once you start getting flow, the more flow you got, the more head loss you got. So the total of the delta Z plus the head loss goes up. Okay. Now, we'll do another problem in which we're going to add a pump to this. And before we add a pump, let's talk about the basic relationships. And this is analogous to the relationships between pipes in series and pipes in parallel, except now we're talking about pumps in series and pumps in parallel. And so if you have pumps in series, the total head across the system of pumps is equal to the head in the first pump plus the head in the second pump. So the total head across these two pumps is just the head in this pump plus the head in that pump, if they're in series, one behind the other. Now the total discharge through this pumping system is the same in both pumps. So the discharge is just the discharge in pump A plus the discharge in pump B. And there's also relationships where you can compute if you know the efficiency for pump A and the efficiency for pump B, you can get the average, the combined efficiency for both pumps working together. And the power, if you know the head being overcome by pump A and the head being overcome by pump B, you can plug that in to get the power. And remember the basic power equation is just power is gamma QH. It's just that in this case there's two pumps, so there's two, you add the H's together to get the brake horsepower. That's the same old power equation, it's just H is HA plus HB. That's for pumps in series. Now for pumps in parallel, the relationships would look like this. If you put the pumps in so that you had them side by side instead of one behind the other, the head across pump A would be the head in pump B. The heads would be the same in the two pumps, the pumping heads. Now the total flow being pumped by the pumps would be the addition of the flow in pump A plus the flow in pump B. And then you could get the efficiency of the two pumps combined, and the power equation is gamma HQ, and so this time it's only one H, but you're adding the Q's together for the power. And this is brake horsepower, so we divide by the efficiency in the conversion of foot-pounds per second to horsepower. Okay. Okay, well, let's go back to the previous example for just a moment. Let's see, where am I here? Nope, got a new example. Well, we'll do this new example. Okay, in this example, it's going to be somewhat repetitious of the new previous example, but it bears repeating the basic concept. The basic concept is the combining of the system head curve with the head capacity curve. And so what we're given here is everything we're given except this yellow line is provided in the basic curves provided by the manufacturer. Actually, you can you got to be given a head capacity curve for the pump and an efficiency curve for the pump from basic hydraulic laboratory data developed by the manufacturer. And then we can actually compute the power versus discharge relationship from the power equation. Now the system head curve, the yellow curve, we got to compute from the system itself. And remember, the head, H sub P, the pump head is equal to the delta Z plus the head loss. And so in this example, well, I can look at it and tell if we're referring to two reservoirs, we got 100 foot of head, and then the head loss using whatever equation we can compute the yellow curve, and then when the two intersect, that gives us a flow rate. And the two are intersecting right here at 710 gallons per minute, and so that gives us the flow rate. If we wanted to know the efficiency for that particular flow rate, 710 gallons per minute, the efficiency, reading off the efficiency curve, I read off 62%. So that's just one pump. Now we want to modify that pump, and so that we're replacing the pump with two pumps operating in parallel. And this is, and we got to go back to the previous transparency now that says when you've got pumps in parallel, and so the example problem says assume the pump of the previous example is replaced by two identical pumps in parallel. Each of the two pumps is identical to the single pump of the previous example. Determine the total discharge rate through the pump pipe system. And so the manufacturer gave us this head curve, which is for a pump. If the two pumps are identically the same, and recognize when you have pumps in parallel, for a given head, the total discharge rate is equal to the summation of the discharge rate through the two individual pumps. And so for a given head, pick a head, any head, let's say 110 feet. For 110 feet, we got a discharge of this amount coming through this pump, and then we got the same discharge, and so I'll add to it coming through the other pump. And so for any given head, the discharge for the two pumps is just twice as much as the discharge for one pump. So the red curve, for any given head, the discharge is just twice as much as this basic single pump head capacity curve. And so for two pumps in parallel, same thing, we got the red curve that's got to intersect the yellow curve representing the system, and where they intersect, I read off 850 gallons per minute for two pumps in parallel. Whereas what did we have for one pump? I think we had 630 gallons per minute. I didn't work out an example, but if you think about it just a moment, what if I had done an example in which the pumps were in series instead of parallel? How would we work that? We've got two pumps in series, so how would we compute the flow rate? If you got pumps in series, what happens is for a given discharge, the head is the head in the first pump plus the head in the second pump. So what we would do there is that for a given discharge, we would take this head. Let's take a discharge of 0. For a discharge of 0, we got a head of 125 feet for one pump, and so for two pumps, it would be twice that, 240. And so for any given discharge, we would double the head, and it would run us off the curve. We'd have a curve way up here. And then wherever that curve, that pump characteristic curve, which would be the head capacity curve for two pumps for two pumps in series, we're talking about now. For pumps in series, for a given discharge, you just add the head in the first pump plus the head in the second pump. And then where the two curves intersect, that would be the discharge rate. But going back to this example, two pumps in parallel, the next sheet is just going through the solution, and it's just saying what I've already said, that for a given head, for two pumps in parallel, the discharge is QA plus QB. If they were in series, we would say for a given discharge, the head would be head A plus head B. And then wherever the system head curve and the pump characteristic curve intersect, that sets the flow rate. And one way you could do it to get the efficiency, for a given pump, we got 850 gallons per minute going through each of the pumps. They're identical pumps in parallel, so there's half of that 425 going through each individual pump. We could go back to the pump characteristic curve And for a flow rate of 425 gallons per minute for one individual pump, you could read off the efficiency of 52%. And this just shows that that is efficiency for both pumps as well. If you plug in the 52%, each pump has 425 gallons per minute flowing through it. Each pump has 52% efficiency. You plug in the numbers, and the two pumps working together have a combined efficiency of 52%. As far as the power, the brake horsepower required to run those pumps, you plug in into the power equation the unit weight of water times the head, and for our problem, we can do it either for both pumps or one pump and combine the power. Let's see, I've done it for one pump, and so let's see, each pump, for one pump we got 425 gallons per minute flowing through the pump. I need a head, and so I'll come over here and say 425 gallons per minute right in there, and I'll read up here to this pump characteristic curve, and I'll get 121 feet for the corresponding head. I'll plug in the 121 feet and plug in the flow rate, plug in a conversion factor to convert gallons per minute to cubic feet per second, divide by a conversion factor that takes foot-pounds per second and converts it to horsepower, divide by the efficiency of 0.52, and I'll get 25 horsepower for each pump, and the two pumps would be twice that, or 50 horsepower. Another way you could do it, put both pumps in, and if you put both pumps in, we've got what's the flow rate through both pumps? 850 gallons per minute, and for both pumps, 850 gallons per minute would be over here, and come over here and read up to the red line for both pumps, and you get the same 121 feet head, and you plug in the numbers and you'd get the 50 horsepower. Okay, and that takes us to the completion of the notes for pressure conduit flow. So we're halfway finished, and I guess we've got less than half of our 3 hours left. We're a little bit behind on time, but we'll do the best. It's not a real problem. We'll just do what we can with open channel hydraulics and pick it up again next week with the time we have remaining. Are you ready to move on to open channel hydraulics, or are there questions or points of discussion?
I still have a lingering question on the example, the pump example, where the efficiency curve ended up going above the head capacity. That first pump problem you worked,
the first one?
Yeah, that first curve where you were at 83% efficiency and 630 gallons per minute.
Okay.
It seems I've got this lingering nagging doubt from when you were talking about cavitation, that you would be in a situation that you'd be so efficient that you would you'd kind of be in the onset of cavitation, because the pump would be so efficient for the given head that you've got. I think I'm missing something there, but...
Yeah, the efficiency just relates to the amount of electrical energy that you expend to provide the hydraulic energy. And what the cavitation relates to is the reducing of the pressure to a point at which liquid water starts forming bubbles of air, or not air, of vapor. And so basically, when we're talking about the cavitation problem, it's a matter of you can't get the pump too high in elevation or the flow rate too great, because of the three forms of energy are elevation head plus pressure head plus velocity head. And so if you get the elevation head too high, it takes away from the pressure head, If you get the velocity head too high, it takes away from the pressure head, and velocity head's directly related to the discharge rate through the system. And so that's basically saying that if the pump gets too high for a given discharge, or if the discharge gets too high for a given elevation relative to the elevation at which the water is coming from, that you'll get cavitation. And so that's not really directly tied into the efficiency. The efficiency is a different concept of electrical energy required to generate the hydraulic energy.
Okay. Okay.
By the way, it's sort of coincidental. The best of this 83% is not because it peaks here, but what we do, we find the crossing point, and for whatever discharge that is, we read up and read off the corresponding value there. And this,
Yeah, no, I was with.
we're very happy about this. The reason we're happy about this is because we selected a pump that's going to be operating very close to the best efficiency point. And we're very happy about that from an economics perspective, because we're minimizing the amount of electrical power.
Yeah. I was with you on that, but I thought you were kind of putting yourself in a situation where you'd be too efficient, but you cleared it up.
Okay.
Yeah.
Other questions about pumps or pipe networks or anything before we move on to open channel hydraulics? We've got 20 minutes left, and so the plan is to do 20 minutes of open channel hydraulics, but we'll be glad to respond to questions too. Now the difference now in open channel hydraulics, we've got the water surface at atmospheric pressure, and in some way that complicates things, in the sense that in pipe conduit hydraulics, and when you're filling up the pipe, you know the geometry of the flow area. But in open channel hydraulics, you don't. The flow area can vary because you're not filling up the pipe. In going through open channel hydraulics, we'll talk about channel geometry first, and then classifying different types of flow. And one type of flow is uniform flow. We'll talk about uniform flow, and then critical flow, and then gradually varied water surface profile analysis. And I think we just moved into next week. I don't think we're going to get that far. And then analysis of hydraulic jumps based on conservation of momentum. So we'll go as far as we can and then pick it up again next week. The first page of notes is really more geometry than hydraulics, and the geometry of the cross-section comes into play, and we're just looking at geometric elements of a channel section. And I picked as an example a trapezoidal channel. Man-made channels are often trapezoidal in shape, and so in the analysis we're going to be interested in the top width. And just using an example, this channel, the bottom width is 20 feet. It has one horizontal and one vertical side slopes. The flow depth is 6 feet. So the width of the water surface, the top width, is 44 feet. And that's just the geometry of saying this portion of the top width is 6 feet times 2. That portion of the top width is 6 feet times 2 to get those end portions, and then 20 feet for the bottom. You get a top width of 44 feet. The flow area would be the top width plus the bottom width divided by 2 times the flow depth to get the 192 square feet. The wetted perimeter, by definition, a wetted perimeter is the distance along the channel section that's in contact with the water. So it would be that length plus the bottom width plus that length. And so the wetted perimeter would be the length of the bottom. And it looks like, what did I do here? I've got another typo that needs to be corrected. We've got 6 feet squared, Pythagorean theorem. And what we're shooting for, we want that length. And that length, this length from there to there is 12 feet, 2 times 6. And that's 6 feet, So if you take 12 squared plus 6 squared, take the square root of that, you'll get the red length. And so you correct that, and then we got this length over here, which is going to be identically the same, so I just multiplied it by 2 to get the wetted perimeter. Then a couple definitions for you. Hydraulic radius, by definition, is the area divided by the wetted perimeter. We computed the area in the wetted perimeter above, so we can divide one by the other to get the hydraulic radius of 4.1 feet. Hydraulic depth is the area divided by the top width. We've computed both of those values above, divide one by the other to get the hydraulic depth. There's actually two depths because